Hi, my name is Beichen Li. I'm a researcher at OpenAI. For this presentation, I'll share my most recent PhD work from MIT CSIL called VLMaterial, Procedural Material Generation with Large Vision Language Models. Procedural materials are essentially programs that produce photorealistic appearances for 3D objects. In the context of Blender, a well-known open-source render, procedural materials are represented as computation node graphs that define shader programs. They output BSDF shaders instead of image-based SVBRDF maps. The nodes are texture generation, geometry processing, or general mathematic operators. The intermediate data in the graph can be textures or numeric values. Blender has a well-established Python API, so we can produce these node graphs by writing Python code. But this is a tedious job even for professional artists. Current state-of-the-art vision language models like GPT-4o can generate Blender Python code given an image prompt, but the results match poorly against input image due to the lack of relevant training data in their stack. We propose to leverage VLM fine-tuning to improve the quality of generating materials. The VLM already has multimodal reasoning and code generation capabilities, but we still need additional data to do the fine-tuning. The SFT training data in image program pairs format are hard to find. There are only a few thousand artist-created materials available online for using. To clean up the data for augmentation, we first find 1.6K free materials from multiple online sources and transpile them into Python code as ground truth labels. The generated programs are checked for correct execution and good rendering quality. Then we adopt an evolutionary workflow from front search to augment the training data. Each iteration randomly selects program pairs from the data pool. A separate pre-trained LLM is prompted to write the example programs into new programs. These new programs are also validated and filtered in terms of execution and rendering quality. We were able to obtain around 50K distinct programs from this augmentation step. The new materials are generally simpler than artist-created ones, but still very meaningful to fine-tuning. Next, we further augment the dataset by 10 times by perturbing node parameters from artist-defined values, resulting in around 500,000 training samples in total. We compare our fine-tuned VLM with other material generation models, including Conditional Matformer and Blender Alchemy. It's worth noting that Conditional Matformer generates procedural materials in Adobe Substance Designer format, which has a broader appearance distribution than Blender materials. We also include zero-shot generalization results from GPT-4o Mini and Nearest Neighbor as baselines. Our model achieves the best result in our synthetic text images. To evaluate the generalization of our method to out-of-distribution material appearances, we incorporate additional test images from Adobe Substance Designer materials and real appearance captures from object surfaces. Our model still achieves the best matching quality against the input. In a separate study, we apply gradient-free post-optimization to the VLM-generated material. This is done with local parameter search using MCMC sampling. We compare the post-optimized material against the vanilla output and the prediction results without our data augmentation steps. The ablated versions show significantly worse matching quality. For more details, please refer to our paper on arXiv. The codebase and training data has been released on GitHub. Thank you for listening.